Hi everyone, this is Kalyan Kumar and welcome to another edition of the solid state videos. Welcome to my channel Chemistry Tutorials in YouTube. Today we are going to look at part 6 of 10. In the last part we did the layer arrangement view of FCC as well as another unit cell which we called as Hexagonal Primitive Unit Cell. Its packing was called Hexagonal Close Packing. And in this video we're going to look at Hexagonal Primitive Unit Cell. In our course of study we need to only worry about cubic and hexagonal. We already done all the three arrangements in cubic, and hexagonal, by the way, has only one arrangement which is primitive, which is what we're going to do in this particular video. So let us start with Hexagonal Primitive Unit Cell. So the hexagonal primitive unit cell, we need to understand its definition. Now, the hexagonal primitive unit cell is a unit cell in which the same type of atoms occupy all the minimum lattice points to generate the least volume unit cell. Now, please try and understand here that the word primitive does not necessarily always mean corners. Primitive unit cell is a unit cell in which the unit cell has the least volume in that particular shape. For example, in the case of cubic, in a primitive unit cell, if you remember, A was 2R and the volume of the unit cell was A cube. Whereas if you look at different arrangements in cubic, for example, body centered and face centered, A was greater than 2R. So if the same atoms were to occupy body centered and face centered, the volume of the unit cell would have been much greater. So the least volume that in cubic shape in a particular arrangement that you have is primitive. So that is how in fact primitive is identified as the least volume of a unit cell and where the atoms occupy the minimum lattice points. So now let's have a look at primitive unit cell. Hexagonal primitive unit cell. Now here I'm going to show you the unit cell shape view. Here of course you will not see which one is in contact, but if you remember the arrangement was ABA, and that is why I have got three layers of hexagon. A layer, one surrounded by 6. B layer had 3 atoms. Of course it had multiple atoms in B layer, but we are only taking the hexagon as the unit cell. So if you look at the ABA arrangement, if I take hexagon as the unit cell, then right on top of this you have 3 atoms of B layer, and then you have again the repeat of A layer. So it is A, B, A. And if you look at the contact points, the atom contact view, this is the A layer, 3 atoms of B layer on top of this in these 7 of the A layer, and then A layer gets repeated. Now here if you look at the contribution, now this being the unit cell, you know that in a hexagon the angle is 120. So the angle is 120, so there will be 3 angles of 120 around a point. So this will be shared by 3 unit cells in which the hexagon is in the same plane, as well as 3 more unit cells on top of each of these. So this is one unit cell in which this is present. There will be another unit cell which will be a hexagon here. There will be another hexagon. There will be 3 hexagons that will share this. So 3 unit cells in one plane and 3 on top of that. So this is being shared by 6 unit cells. So its volume that is present in one unit cell is going to be 1/6. And this being the face centered, this is half inside and half outside. So its contribution is half. And these are the 3. So if you look at the total rank of this particular unit cell, it is 1/6 into 12, there are 12 corners, half into 2 plus 3. So let's have a look at that. The volume that a corner sphere occupies in the unit cell will be 1/6 of its volume. The volume that a face center occupies is half of its volume, and the volume occupied by the B layer atoms is 3. So the total rank becomes 1/6 into 12, 1/2 into 2 plus 3, that is 6. So here the rank that we are getting is 6. Now let's identify the relationship between the various lengths, width and the height of the unit cell with respect to R. Now we are going to call this as A, this is B. If you remember the hexagonal shape, hexagonal unit cell, A is equal to B, not equal to C, and the angle here is 90. The angle between these two is 90, but the angle between these two is 120. So A, B, C, and gamma is 120, alpha and beta are 90 degrees each. So let's have a look at the lattice parameters. So A is 2R because remember they are in contact. This is in contact with the 6. Can you see these two are in contact? Or rather these two are in contact and these are these two. So A is 2R, B is also 2R. We need to find the height. So this is the unit cell, the hexagonal unit cell. A was 2R. Now let's find the height. To find the height, what I'm going to do is I'm going to look at these three atoms, and this atom is actually sitting on top of these three. Now I'm going to calculate the distance from this point, the central point of this face centered, to the midpoint of this hexagonal layer. So if this total height is C, then from this point onwards to this point it is C by 2. So I'm going to calculate what is that C by 2. So the three atoms that I'm going to talk about are these. This is the B layer atoms, and the A layer is sitting on top of this atom. And the distance from the center of the top sphere to the center of this void, which will be in the plane of the hexagon, that will be C by 2. Now we know from trigonometry that this is an equilateral triangle. And if I join the center, this is the center of the triangle. If I join the center of a triangle, of an equilateral triangle with one of the vertices, then it also becomes an angle bisector. So that's 30 degrees. So B, A, C and D and O, and this angle is 30 degrees. Now from again trigonometry, we will notice that AD is R and AO is the hypotenuse. So base over hypotenuse, AD over AO would be cos 30. And since I know AD is R, AO will be ADO upon cos 30 or R upon cos 30 or R secant 30. And secant 30 is 2 by root 3. So AO is 2R by root 3. Now that is this hypotenuse AO. Now let's transform all these points in the unit cell now. This is O, this point is O, O is right at the center. This point is O, this point will be A, and I'm going to join the center of this sphere with the center with this O, which will be C by 2. And this is the hypotenuse OA or AO. Remember that we calculated this one, that is why we calculated that. And this is the hypotenuse that is joining the top sphere. And let the top center be E. Now AE is 2R because remember this is in contact with these three. This has been placed on top of these three. So these two are in contact. So EA or AE, this EA is going to be 2R. I want to calculate EO, which is C by 2. I already know what is AO. So I need the height. I got the hypotenuse, I got the base. So the hypotenuse is 2R. So according to the Pythagoras theorem, C by 2 should be equal to the root of 2R square, which is the hypotenuse square, upon the base square, which is 2R by root 3 the whole square. So it's going to be minus that. So 2R square minus 2R by root 3 the whole square, under root of that would be EO. So EO is C by 2, which is under root of 2R square minus 2R by root 3 the whole square, which is 2R root of 2 by 3. So if C by 2 is this, then C will be 4R root of 2 by 3. So let's go back to our master slide. So this is what the next point talks about. It says that the contribution of each corner sphere is 1/6 for a unit cell, the contribution of face center is half for the unit cell, the contribution of second layer is 3, rank is 6, A and B are 2r, and C is 4r root of 2 by 3. Now let's look at something else now. Now here what I'm going to talk about is, I'm going to tell you right now that this is not hexagonal primitive unit cell. That is because, remember, the unit cell's definition has to be the smallest repeating unit along with symmetry. Well, this hexagonal unit cell can be broken into 3 pieces. Just look at these things. I'm going to join these two. I'm going to join these two. Same will happen here. Join these two, join these two. Then I join these 2 points. And now I'm going to join these two. I'm going to join these two. Suddenly you will notice hexagon has been broken into 3 equal pieces. And it is this small piece which is actually the unit cell, because it has got to be the smallest repeating unit following all the symmetry elements. And this is actually a rhombus. They're all 2r, but their angles are not 90. This is 120, this is 120, this is 60, and this is 60. So this rhombus based thing is the actual unit cell. So this is what the actual unit cell would look like. Now before we go any further, I need to check one more thing. I want to make sure whether these 3 spheres lie within this hexagon or are they somehow coming out or not. To test that, what I'm going to do is I'm going to take these 3 spheres, and I know that this fellow is sitting on the void of these 3. So these 3 spheres are like this. This is the A layer spheres on top, okay? And this fellow is sitting over here. So I'm going to calculate. Now remember, the hexagon has been made by joining the line here, the center of these 2. So the center of these 2 is where the hexagon ends. This is where the hexagon ends. And now I want to know whether this entire sphere is within this line, because remember, this line is just below this line. So I want to check whether by putting an atom at the center here, is this atom going to come out of the hexagon or is it going to stay within the hexagon? So the hexagon ends with these 2 lines. So let me draw the triangle. This is the line of the hexagon, okay? And I'm going to place a sphere here and test whether the sphere comes out of this hexagon or not, because if it does come out, then remember we have already taken the contribution of these as 3. So if this comes out, then obviously its contribution is not going to be 1, and therefore the contribution of these 3 also is not going to be 1 each. So we might have a problem with the rank. So let's check that out. Now again, this is the triangle, equal to triangle, angle bisector A, D and O. This angle is 30 degrees. And I want to check what is OD, which is the center of the void to the place where the hexagon ends. Now from logic, we know that AD is R, okay, and the angle is 30, so we need to find the height. So the OD, the height over the base, is tan 30. OD by AD is tan 30, and AD is R. So OD is R tan 30, and tan 30 is R by root 3. And that is a problem for us now. If it is R by root 3, that means, now just have a look at this. If this OD is R by root 3, if I place a sphere with its center on O, remember the sphere is going to end at a distance R, and this is only R by root 3. So from the center here to this point is R by root 3. Therefore this fellow whose center is sitting right on top of O is going to come out of the hexagon. It will be like this. And therefore we have already taken its contribution as 1, which is a problem now. So how do we manage this? If the contribution of these 3 is not 1 each, then how did we take this as 3? Because it is based on the fact that these 3 have a contribution of 3 that we actually said the rank is 6. But there is no need to worry, because the point is in fact that whatever amount of this is coming out, remember a similar amount of sphere will come in from the next unit cell, from the one which is behind this. So whatever part is going out is going to come in. Whatever part of this is going out here is going to come in from here. Whatever part of this is going from here is going to come out from here. So whatever part is going out is also coming in from other sources. So the total contribution still remains 3. So our rank is safe. It is still 6. That's why if you remember, if you go back in the video and check, I never said that the contribution of these 3 atoms is 3. I said the contribution of B layer is 3. So the contribution of this entire layer is 3, not that the contribution of each of this is 1 each. And the unit cell, this particular shape that we saw, rhombus shape, well, I'm going to show you in 2D. This is A layer. These are some of the atoms of B layer. And the rhombus is formed by joining these. So rhombus is formed like this. Now look at the B layer atoms. Can you see that this entire big sphere, a part of it is going out? A part of it is going out, but similarly a part of something else is coming in. Whatever part is going out is coming in. Whatever part of this is going out is coming in. So this total contribution is actually 1. Now remember, since we have broken the entire unit cell into 3 pieces, so everything becomes 1/3. All the extensive properties become 1/3, the intensive properties remain same. Now the height will remain the same, 4r root of 2 by 3, but the rank becomes 2. Because the rank of the overall was 6, broken into 3 pieces now 2. And how is it 2? Very simple. Now this angle is 120. This is shared by, remember, 6 unit cells. So its contribution is 1/6. So will be the contribution of 1/6 because this is also 120. So 1/6 into 1, 2, 3, 4. 1/6 into 4. Now 1/6 into 4 is 2 by 3. Now this angle is 60. If this is 60, then in one plane 6 unit cells will share and then 1 on top of each. So this will be shared by 12. So 1/12 into 4. These two and these two. So 1/12 into 4 is, you can calculate, 1/12 of 4 is 1 by 3. So 1 by 3 into this, each is 1 by 3, remember. This is shared by 6 unit cells, 12 unit cells. Its contribution is, now in this 1, its contribution is going to be 1/12. 1/12. So this is going to be totally 1 by 3. These two contribute 2 by 3. Essentially the contribution of all the corner is 1. And we've already seen contribution of B layer is also 1 because whatever is going out is coming in. So the total rank is 2 in this particular case. So let's go back to the master slide, which is what it is going to exactly tell us. So the master slide says that the actual unit cell is 1/3 of the hexagonal shaped unit cell and the actual rank is 2. Now let's look at the packing fraction and let's see what the packing fraction is all about here. Packing fraction is the total volume occupied by the atoms in the unit cell upon the volume of the unit cell, and that is going to be rank of the unit cell into volume of an atom upon volume of the unit cell. Remember, I'm calculating it for the bigger one. For the bigger unit cell, it is 6 because the intensive properties will remain the same. So if I take the rank as 6, then 6 into 4 by 3 pi r cube upon the volume of the unit cell. So 6 into 4 by 3 pi r cube upon the volume of the unit cell. Now how to get this as the volume of the unit cell? Remember, this is going to be the height, C. So now it is base area into C. Now the base of a hexagon can be broken into 6 equilateral triangles, and each equilateral triangle has a area of root 3 by 4 a square, and a is 2r if you remember. So root 3 by 4 2r square. There are 6 equilateral triangles. So this is the total base area. Base area into height is the volume, and when we calculate this, magically this figure comes out to be the same as face-centered cubic, 0.74. So the packing fraction of hexagonal primitive unit cell is 0.74. This means 74% of the unit cell's volume is being occupied by the spheres, and 1 minus 0.74, that is 0.26, is called the void fraction. This means that 26% of the unit cell's volume is empty. Hexagonal primitive unit cell therefore has the highest packing fraction of all the unit cells. The same thing that we said for face-centered. No unit cell other than face-centered and hexagonal primitive can have a packing fraction of more than 0.74. So let's go back to the master slide, which is going to tell us exactly the same thing, and that is that each atom in hexagonal primitive unit cell is 0.74. The packing fraction is that. Let's look at the coordination number. The coordination number, well, this is my A layer, and you will notice there are 3 atoms of B layer which come. Now in this A layer, this is in contact with 6. I'm looking at the central one. This is in contact with 6. So already 6 it is touching. It is touching 3 from the top of B layer, and it will touch 3 from the bottom of the B layer. So it is AB repeating. So each atom touches 12 atoms. So the coordination number of hexagonal primitive unit cell is 12. And the density of an HCP unit cell, as you know, is again the same logic. Mass of the unit cell upon volume. Volume we already figured out. Mass is atomic mass upon the Avogadro's number. 6 is the total number of atoms. This is the density of the bigger unit cell, the one with the hexagon shape. But since density is an intensive property, it will remain the same. So now what I'm going to show you is, I'm going to show you a 3D view of how the hexagonal primitive unit cell, the smaller one, the rhombus one, actually looks like. So this is how it looks like. Let me show you the 3D view, and this is the 3D view. Now look at this, the rhombus, this angle is 60. Can you see how less the sharing is? And this angle is 120, the sharing is greater. But more interestingly, look at the middle part. Can you see this big atom here, which is so unevenly cut? One part is cut from here, one part is cut from here. Remember the B layer had 3 atoms? But whatever part of it is going out, the similar equivalent part is coming in. In fact, this was the amount of the B layer part of that bigger atom that was cut off on 2 sides. And from 2 sides, we have those smaller parts coming in. The total contribution of the central atom is going to be 1. So whatever part was going out, look at this again. Whatever part was going out, these 2 parts were going out, and they are coming in. They're coming in from 2 other sides. So this is the 3D view of the hexagonal primitive unit cell in its native state. So that is the end of this particular video, part 6. In part 7, we are going to talk about more on solid state. And I hope you understood whatever I talked about in this video. Please subscribe to this channel if you haven't done already. Your encouragement really matters a lot. The more you subscribe, the more I get motivated in making such videos. If you have any comments, queries, any doubts, any question that you want to ask, please drop them in the comment section below. This is Kalyan Kumar signing off. Have a great day, and thank you for watching.